As a conclusion, what I'm saying is that momentum measures the amount of motion. It measures how difficult or how easy it is to stop a moving object. The topic of mechanics in grade 12 is an extension of Newton's laws we studied in grade 11. Mechanics in grade 12 focuses on two concepts: momentum and impulse. Lesson 1 will study linear momentum, sometimes called momentum. Momentum can be defined as the product of the mass and velocity of the object. Let's break down the definition of momentum. The word product, we know from mathematics that it means that the number that we get after multiplication. So in this case, we're saying that if we multiply the mass and the velocity of the object, m times v, the number that we get is called momentum. Hence, it is given by the formula P is equals to mv. In this formula, the m represents the mass, which is measured in kilograms, kg. The v stands for the velocity, and it is measured in meters per second. The symbol for momentum is given by the letter P, and the SI unit is kilogram meters per second. To understand where this SI unit for momentum comes from, let's take a situation where we use the formula m is equals to mv of momentum, wherein we're going to substitute the SI unit of the mass as kilogram and multiply that by the SI unit of velocity, which is meters per second. We will end up with an SI unit that says kilogram meters per second. It's a combination of the SI unit of mass and that of velocity. Now, this is to say that if you have an object that has a mass of m and a velocity of v, if you combine these two, the mass and the velocity, by multiplication, you're going to get the momentum p. So this diagram shows an object that is moving with this velocity to the right, and it has the momentum that goes to the right. There are a couple of things that we need to learn here. From the formula of momentum, we see that momentum is directly proportional to the velocity. In other words, if the velocity of the object increases, the momentum will also increase. If the velocity of the object decreases, the momentum will also decrease by the same ratio. Let's look at different scenarios to explain this direct proportion. Remember, we said directly proportion means that the two quantities increase by the same ratio or decrease by the same ratio. Let's say in the first instance, we have an object that has the mass m of the ball is equals to m. And this object, let's say it has a velocity of v of the ball is equals to, let's say we give it a number v. So what are we saying here? We're saying we have an object which is a ball, the mass of the ball, then we say that mass is m. Then we say this object, it moves with a velocity v, right? Velocity of the ball is equals to v. If I were to calculate the momentum of this object, it will be given by p is equals to mass of the ball times velocity of the ball. That is the formula of momentum as we define momentum, is the product of the mass and velocity. Now we said that the magnitude of the mass is m. So this will be given by m times the velocity. We say here that it's v. So this will be v. So this means that the momentum of this ball is equal to mv. Now to explain direct proportion, suppose that the same object which has a mass of the ball is equals to m. Let's say now it moves faster, meaning the velocity now has been increased. So that we have a new velocity of the ball. I'm going to call it v prime. I'm going to use a dash at the top to say that it's not the same as this velocity. We have a longer velocity now. This object is now moving faster. Let's say it's moving by 2 times the original velocity, meaning this velocity here is twice this velocity, is twice v. It's moving faster, twice as fast compared to the first scenario. Now in this case, if we were to calculate the momentum, it will then be given by p prime. I'm going to write p prime here because this velocity is not the same as this one. The velocity has changed in this case. We're not going to get the same value. Now this means that here I'm going to have mass of the ball times velocity of the ball prime, because the velocity now is vb prime. It's not the same as the original velocity. Now in this case, when I substitute, I'm going to have m times 2v, and this will simply give me 2mv. Now at this stage, I can group the mv together by putting brackets like that, so that now you can see that I'm going to have 2. Notice that the mv, it is this p here because mv is the same as p. So this means now I'm going to have 2p. That means my new momentum p prime is equals to 2v. What does this mean? This means that if I double the velocity, the original momentum that I had will also double. I'm going to have 2p as well. That is a direct proportion. As one quantity increases, the other one increases. As the velocity increases, the momentum also increases. But they increase by the same ratio, which is 2. They increase by the same number of 2. Another scenario that we can study to explain direct proportion is that when the velocity decreases, because remember, direct proportion means increase and decrease. In this scenario, we still have our mass m of the ball, mb, is equals to m. And we're saying here that our velocity now has reduced. I'm going to call this v b prime prime. I'm going to use double dash here to say this velocity is not the same as this one. Now in this case, let's say it is reduced so that it is 1 over 2v. We have half of the original velocity. Then we have a smaller velocity according to how I've drawn that vector. Now, in this case, if I were to calculate my momentum, it's going to be p prime prime. To say that it's a new momentum, it's not going to be the same as here. It's also not going to be the same as in the first scenario because our velocity has been halved. Now, according to our formula, this has to be the product of mass and velocity, the product of the mass of the ball times the velocity of the ball. But this velocity now is prime prime because it is not the original velocity, it is not either the velocity in the second scenario. Now in this case, we are going to have the mass as it is, but here we're going to have 1 over 2 v. Now this can be simplified to be 1 over 2 mv. Again, like we did in this first part, I can group mv by putting brackets like that, because I recognize that mv represents the p, is the same as p here, what we found in the original situation. So this would mean that my new momentum, when the velocity is halved, is going to be half the original momentum. Half the original momentum. Again, we see a direct proportion relationship here to say that if you halve the velocity, the momentum will also be half. Alright, so if you decrease the momentum, the velocity, the momentum will also decrease by the same ratio, exactly the same ratio, 1 over 2. So this will be true with different ratios. This can be 1 over 4, it can be 3 over 4. Also here you have to have 1 over 4 or 3 over 4. This can be 4v, also this will be 4v, it can be 10v, also this will be 10p, in that order. So you have to see that direct proportion relationship. That is the first property that we have to see with momentum. Momentum is directly proportional to the velocity. The other relationship that we have is that momentum is also directly proportional to the object's mass. This again would mean that if the mass of the object increases, the momentum will also increase. However, you have to note something very important here. When we have a scenario like this, the mass is not allowed to change. In other words, our formula of P is equals to mv as we defined it here, the mass should not change, it's always a constant. The mass of my object will not change, will always be a constant. The velocity might increase or decrease, that's fine, but the mass should not change. So what does now this relationship entail? Why do we need to see this relationship? So this relationship is important because it will help us to study momentum when we compare different objects. How do I mean? Suppose we have a box. That has a mass of the box to be given by 2m. So what am I saying here? I'm saying the mass of this box is twice the mass of the ball. It's twice as big. So these two masses are in proportion, right? Here we have 2m. So if you take 2 of these balls, they'll give you exactly the mass of this box. And let's say that now this box moves at the same velocity, v of the box to be v, at the same velocity as the ball. Now, if I were to calculate the momentum of this box, I'm going to have momentum of the box is equals to mass of the box times velocity of the box. And when I substitute here, I'm going to have 2m multiplied by the velocity v. And this will give me 2mv. Now, if you check this momentum, it has a relationship with the momentum of this ball here, because the momentum of this ball is given by P is equals to mv. Remember, I'm multiplying this and this, then I get the P. So you can see that from this point here, we then again have a relationship where we can group the mv so that our momentum of the box is equals to 2p. Do you see that? So we're saying that if you double the mass now, the momentum will also double. It is double this momentum that we started with on this object. So this relationship here allows us to compare two different objects when they are in proportion, when their masses are in proportion. Not necessarily that this mass will change. This mass can never be 2m here. We cannot increase this mass to be 2m. It is not possible. This cannot just enlarge and be big. So we use this relationship to compare one object from another, the momentum of one object compared to the momentum of the other object. So we see that we still have a direct proportional relationship. When you increase the mass, the momentum will also increase. It will be 2m. So the original momentum we started with here is 2m. The same can be said with decreasing the mass. Let's say you have a trolley. Let's say you have a trolley that has a mass of m of the trolley is equals to 1 over 2m. So what we're saying here is that the mass of the trolley here, it's in proportion with the mass of the ball. It's half this mass. Meaning that if we were to reduce the mass of this ball so that it is smaller by half, it's a smaller ball, right? What will happen to its momentum? But because we know that this mass cannot change, it means we can apply that in comparison to another object that has half of that mass. And in this case, I'm going to also assume that the velocity is still the same as that of the ball. So we assume that the velocity here is also the same. Now, this would mean that if we were to then come and say momentum of the trolley, it will be Pt is equals to mt times Vt. Now, this would mean that I now have 1 over 2 m, and I'm multiplying this by a v. We can further simplify this to be 1 over 2 mv. In the same way, we can group the mv so that we know that the mv represents the p that we had here, because p is equals to mv. And now this would mean that the momentum of the trolley is equals to 1 over 2p. And again, we see the direct proportion. If we halve the mass, if we take a smaller object compared to this big object of m, because it's 1 over 2m is half of this, the momentum will also be half. The momentum that we used to have here will be half. Now, on all these problems that I'm doing here, or scenarios that I'm looking, you have to also note that when I change the mass, when I start with the mass of m and I do half of the mass, or I do double the mass, the velocity is constant. It does not change. It's the same. We use the same velocity v. That is important because it ensures that the mass and the momentum will be in direct proportion. They will both decrease or they'll both increase. You cannot change all these parameters all at the same time. Just to emphasize that point, let's also look at these first scenarios that we did. The same thing here, when we were changing the velocity here, so this one here, we were changing the velocity to be 2v from a v. We made sure that the mass doesn't change. We're using m the way it is. It was not changed. The same is true here. When we changed the velocity to half v, the mass didn't change. It was still m as it was in the first scenario. So when you do a direct proportion calculation, it is important that one of the quantities should be constant to ensure that the direct proportion occurs. We call that the constant of proportionality. The quantity that will remain constant, we call it the constant of proportionality. The other property of momentum that you have to notice is that it is a vector quantity. And this is because it depends on the velocity, the vector quantity. Remember that the V on the formula stands for velocity. So if you multiply m, which is a scalar quantity, and v, which is a vector quantity, you're going to get a vector quantity. And because momentum and velocity, they're directly proportional, this means they'll go in the same direction. That's why when you look at these scenarios, the velocity goes in this direction and the momentum also goes in that direction. They point in the same direction. So when you give your answer for momentum, always report the direction as well. And just a reminder and revision, a vector quantity is a quantity that has both the magnitude and direction. In other words, you're going to write the number, the value, and the SI unit and include direction. Maybe you'll say that it's 2 kilogram meters per second to the right. Whereas a scalar quantity like mass is a quantity that has only the magnitude but no direction. You only write the magnitude like 2 kilogram without direction. At this stage, one may be interested in understanding or asking a question that why do we study momentum? Is momentum important? How does it help us to study momentum? Momentum is an important concept because it helps us to distinguish a big object and a small object that are moving with the same velocity. How do I mean? Suppose that you have a bus and a tennis ball. Clearly we can see that the bus is big in terms of mass and the tennis ball is small. Now we're saying that these two objects, they move at the same velocity. So let's say the velocity here, I'm going to choose this as the velocity of the bus. Let's choose maybe 5 meters per second. And also the ball, let's say it has the same velocity, right? So the velocity of the tennis ball is going to be 5 meters per second. And as I said, these two objects have different masses. This one is big and the other one is small. So let's say the mass of this object here is going to be mb. The mass of the bus is going to be, let's say, 8,000 kg. And obviously this is a small object. Let's say I'm going to say the mass of the tennis ball, let's say, is going to be 0.5 kg. Now, if I were to compute the momentum of the ball, it is going to be given by the momentum of the bus. Let's start first with the bus. It's going to be mp is equals to pb is equals to mb times vb. And this would then give me the momentum of 5 is going to be the mass of 5 and the mass of 1,000. Now this would mean that my momentum would be a 5,000 kilogram meters per second, and this goes to the right. Now this is how you would fully write your answer because it's a vector quantity. It has the magnitude and the direction. Now this is to say that if I were to draw a vector that represents this, it's going to be a long vector like that. That represents the momentum of the bus. So you can see here that we have a big momentum. Now if we compute the momentum again on this side of the tennis ball, is going to be pt is equals to mt times vt, so that I have the 0.5 multiplied by 5 because they have the same velocity, remember. Now this would mean that I'm going to have a 2.5 kilogram meters per second, and this as well goes to the right because we report the magnitude and direction, because momentum is a vector quantity. Now, if I were to draw this vector, you can see that this number is small compared to this number. So my vector would be a small vector like that. Momentum of the tennis ball. Now, it is clear that a big number would tell us that we have a big amount of motion here, and a small number will tell us that we have a small amount of motion. This means that if I were to try to stop the bus from moving, if I were to stand here and try to stop the bus from moving, it will be extremely difficult, if not impossible, to stop the bus, because it is big in mass and also it is moving, even though it is moving at a smaller velocity. But it will be practically impossible to stop that bus. We measure that by the momentum. The momentum is big. That's why it's difficult for me to stop that bus. So we're saying it has a bigger amount of motion. On the contrary, if I were to try to stop this ball, it will be much more easier because the momentum is small. It's a small object and it's moving at a small velocity. I'll be able to catch it and stop it. So the amount of motion here is small. So if you want to know the amount of motion of an object, you basically look at two quantities. How big is that object and how fast it is moving? The two combination will give you the amount of motion.